Hello, how's it going? Welcome back to Computer Science 4300. I've got some visitors in my room that I'm going to show you before we get started. Here's one crawling on a stack of exams. This is Enzo. He's grown up a lot since the last time you saw him. See if we can get the focus there. There's Enzo. He's gigantic. And oh, this is his sister. Say hello. Say hello, Stella. It's two little kitties. They've grown up since the start of the term. They used to be so tiny. And now he's about twice the size of her. It's crazy. Okay, let me go put them. I'll be right back. Oh, now they're crawling on the desk. Give me a second. Okay, here we go. Where's my mouse gone? There's my mouse. All right. Yeah, so welcome back to Computer Science 4300. Today, where are we? We talked about the course project last time. I see a few people using the LFG channel to try and find a group for the project. That's great. So please keep trying to do that. Just remember to remove your name, remove your message once it's done. Otherwise, a bunch of people are going to keep messaging you for a group once you've found one. So today, what are we doing? We are talking about pathfinding and steering behaviors. So rather than wait any longer, let's just, oh my god, I'm out of breath from chasing around kittens. So I'll be panting for a little bit. All right, here we go. Time for the slides. Oh no, one second. My slideshow view is pointing to the wrong monitor. There we go. Perfect. That setting of which monitor your PowerPoint goes to took me like 10 minutes to find the first time. It's crazy. Fixing one more thing, and here we go. So, lecture 15, pathfinding and steering behaviors. What is all that nonsense about? So movement in games, we all know what movement is, but movement is arguably the most important part of a large number of video games, right? If your movement feels bad, your game feels bad. I can't count how many games that I've played where it's like, oh, if they had just like made this a little bit nicer, you know, the movement a little bit nicer, the game would be so much better. So it allows for the exploration of the game world, obviously, the interaction with entities, etc., etc. And not only does the player move in the game world, but the NPCs and the entities do as well. And so those NPCs and other entities have to move somehow, and they have to find their way around in the world. And so not only is there movement for the player, but there's the movement for all of the non-player characters in the game world as well. And in my opinion, good movement makes a good game. So we should probably take a while to make our movement system. So, the main video game movement problems. What are the movement problems? Well, there's pathfinding. That's the first problem. And pathfinding is how do we get from spot A to spot B in our game world? So what is the path that we would want to take in order to do that? So that is path finding. Then once we have the path, the thing that often gets overlooked is actually path following. So now that we have the path, how do we actually move along that path, right? And we'll talk a bit about that later in the lecture. Next is the physics, so how the environment interacts with us moving around. So for example, do we collide with the environment? Are we flying around? Are there collisions? All sorts of things. And in many, many games, there is also animation associated with movement. So for example, how does our entity look when they are walking? How are they animated? If it's a 3D game, for example, like the Dark Souls series of games, if I'm moving in one direction and then I switch directions, there's a complicated series of animations that have to play in order for me to like realistically feel like I'm turning from one point to another in the game. And so in this course, we're going to be doing path finding and path following. Well, we're not going to be doing them. We're going to be talking about them. The physics of movement, we've talked about a little bit. The animation of movement, this is not an animation course, and so we're not going to be talking specifically about how enemies or entities look or transition their movement as they walk around in games and stuff. In this lecture, we're going to deal with decision-making for movement. So decision-making meaning the path-finding stuff and the path-following stuff. But I don't want to spend too much time of this course on path-finding and path-following, because the games that we're making are fairly basic in terms of AI. This would fall into the category of AI, is decision-making for pathfinding and path-following. And we actually have an entire other course, which is Computer Science 4303, which deals with AI in games. And so I didn't want to have these two courses overlap too much. But let's give a few examples of pathfinding and why it's important. Here's an example from the Saints... What's going on here? Can I click? I gotta get rid of my laser pointer, I think, in order to click. All right, so this is a pathfinding example. Oh, I gotta turn off my sound. From the Saints Row series of games. And so let me turn on the sound here. And you can see here that the pathfinding in the game doesn't really take open bridges into account. Oh my god, that's loud. I'm gonna turn that off. So here we see that the pathfinding, sort of this like 3D pathfinding problem, where the cars have been told, hey, this is the road that you should take to get from point A to point B, but then this drawbridge goes up, and it's kind of a funny example of when pathfinding breaks in a video game. But of course, the Saints Row games are kind of like, what do you call them? Like a satire on GTA-like games, and so it may have been actually intentional that they did something like that. This is another example of when pathfinding in a video game can go a little bit wrong. And so what you'll see here is this is an example of Skyrim, and in this game, it's notorious. This says threat-aware pathfinding up in the top right. So when the NPCs hear the user or hear the player walking through the level, they'll say like, oh, what's that? And then they'll go like try and find them. So you're sort of invading this nest of bandits here. And then something really funny happens when the pathfinding system kind of doesn't take threats into account.
Is someone there?
So here the user is sneaking and hiding so the enemy can no longer see us. The enemy is going to come around the corner here, and the enemy forgot that there's this trap right next to their home, and so they walk down and then get crushed. And then this guy comes along and totally didn't see what just happens, and they get crushed. And so, you know, there's a lot of interesting ways that, yeah, must have been the wind, right? There's lots of interesting mechanics in Skyrim that people often make fun of the AI for. There's also multi-agent pathfinding. So for example, here are two examples from the original game of StarCraft Brood War, where multi-agent pathfinding kind of doesn't work as intended. So this example down here is an example where you have an army, let's say you have a group of tanks, And so you select all your tanks and you tell them, I want to move to this other part of the map. Now, ideally, what's going to happen is that you're going to do some sort of multi-agent pathfinding to try and keep that group of units together as they move. But what you're going to see is that's not what actually happens in the game engine. In fact, if I tell all these tanks to move in the Brood War game engine, it actually forms a single path from the start to the goal, and then all of the entities sort of just try and fight for position on that path. And so now what you can see by the middle here, if I can unpause this once it gets to that spot, you've actually got this nice formation of tanks, which is now a straight line of tanks. And if you've ever played an RTS game, you know what happens when your units form a straight line like this. They're going to just get picked off one by one. And so they form this line, and the enemy, if it was here, could have easily just destroyed the tanks one by one. And then only when they get to the destination do they try and group up again. So that's kind of a bad example of group pathfinding. Next, I have this example where I'm telling a bunch of entities to surround and kill this building. But you can see here that they're kind of getting stuck on each other, right? And so this business of getting stuck is the plague of any game when it comes to multi-agent pathfinding. And so this, I mean, it does a decent job eventually, but you can see here that it took about 20 seconds to actually surround that building and start attacking it. So that's a bit of an issue. Here's an example from StarCraft 2, and StarCraft 2 had a way better pathfinding system than StarCraft 1. I mean, it was like 12 years later, or maybe even, yeah, I think it was 12 years later that the game came out. So you can see here, we can select our group of Zerglings and tell them to move around, and they do actually keep this sort of flocking behavior, and they stay together as they move. And you can see, like, I can't really imagine a better result in a multi-agent pathfinding system than what's happening right here. Like, they stay together pretty well. The next thing that is again covered up by my face is realistic behavior. So even if your paths are good, you've still got to make the animation system and the path following system look realistic. And here we have an example from Dragon Age where there's some sort of bug in the pathfinding system when it gets to its destination, and all the NPCs just keep moving around, and they don't think they've found their exact destination yet. And so that can be really distracting from gameplay, right? You probably don't want to have something like this in your game engine if possible. That being said, the pathfinding in Dragon Age was actually quite good, and I've definitely cherry-picked this example of something going wrong. And not only realistic behavior, but you'd like realistic paths. So down here, you see this NPC just started running towards us, but as soon as we ran up on top of this house, that NPC is now taking a completely different path. And so this is kind of a funny example of how, ideally when you do pathfinding, you're taking the shortest path, but this is definitely the longest possible path. So this NPC is still trying to find us. It's going up and around the level. This is from the Fallout series of games. Obviously, Bethesda has a sort of track record when it comes to wonky AI sometimes, but that's part of the charm of their game, in my opinion. And up here, finally, this NPC reaches their destination. So they're trying to deliver this package to us, and they went all the way around the level. And when I said that animations matter as well, it certainly does. You can have the most clever path in the world, but if your horse is stuck in this animation as it's moving around, you're just going to get clips like this posted to Reddit, and everyone is going to make fun of your game, right? So that's kind of funny how important animations can be as well. So let me just play that once more because it was pretty quick. But yeah, realistic animations are going to matter in your movement system as well. So we identified those 4 problems, the first of which was pathfinding. So we'll talk about pathfinding a little bit. If you've taken the 3200 course with me, you will find some of these slides familiar. But if you haven't, then this is all going to be new to you. So video game maps are often filled with obstacles with which NPCs will collide, right? So if your map was just one big open soccer field, then pathfinding would be an easy problem. You just move in a straight line from point A to point B. But in most video games, that's not the case. We're going to have obstacles like walls, maybe other entities, maybe like there's some bomb in the middle of the map or something you want to avoid. And we're going to collide with those. It's going to look bad. And so our pathfinding system, maybe we have some sort of maze-like structure, should ideally be able to like work its way around those obstacles. So pathfinding is the method we use to determine which path an NPC should take to go from its current location to a goal location. So the two inputs to a pathfinding system are where am I right now and where would I like to reach eventually. Pathfinding, typically, those systems attempt to minimize some sort of cost on a path. So that cost could be a number of things. Typically, it's the total path length. I would say that 98% of pathfinding algorithms are going to be minimizing the distance toward a goal. But that could also be something like minimize the fuel to my final destination, or the damage taken, or any other arbitrary function. A student of mine and myself wrote a paper, I think 2 years ago, that had to do with pathfinding, but sneaky pathfinding, meaning find me the path that most avoids being seen by the enemy. So we would take a much longer path if it meant that we wouldn't be seen by the enemy, because we were trying to do like sneak attacks and stuff in video games. So that was an interesting problem. Some of the considerations you have to take when doing pathfinding, there's a bunch of different things. So there's single and multi-agent pathfinding. So single agent pathfinding, you're just trying to take one agent to a destination. Multi-agent, obviously, we've looked at that already. We're trying to take multiple agents to a destination. Not only can there be single and multiple agents, but there could also be single or multiple goals, right? So for example, I want to reach the end of the stage. That's a single goal type of problem. But I want to get to the closest health pack. That's a multi-goal problem, right? So you can consider like one of the hardest things to do is, let's say we have 10 different agents and we're trying to say, okay, those agents should all get to the closest health pack. And that might be a very difficult problem to solve. We could also have static pathfinding. So whether or not we want all of our paths to be pre-computed before we play the game, or do we want our paths to be dynamic, meaning that they're generated online as the game is being played? Most stuff you would want to have sort of a dynamic pathfinding system, but there are cases where you have certain games that are on grids where you could pre-compute a number of paths and then just follow those pre-computed paths later. You also have to choose your space representation. So for example, what is the data structure that represents the environment that your algorithm, excuse me, I got the hiccups today. What is the data structure that represents your environment that your algorithm will actually run on, right? So do you have this sort of like open, just arbitrary floating point representation? Maybe you have a grid representation, or maybe you have a graph, maybe you have polygons, etc. And I'll show some examples of those a little bit later. Also, you have to talk about your movement directions, right? So do you have fixed movement? For example, can I only move up, down, left, and right? Maybe I have arbitrary angles and movement. Maybe I have nodes on a graph, right? So fixed movement might be something like the original Zelda, like top-down sort of thing, right? Where you're playing this action RPG, I can only move up, down, left, and right. Many more modern games have arbitrary angled movement. If you're thinking about like Path of Exile, I can click anywhere on the map and it can run in any direction, any angle. Or if I'm thinking about like Civilization, right? Civilization is literally played on a graph. So it's the best example of this, where if I want to move my scout to go look at the enemy, I'm literally moving between nodes on a graph, actually a hexagon graph when it comes to Civilization. So let's look at some of the examples of these. So pathfinding, we have the example of single agent, single goal. So if I have a single goal, a single starting location over here, and I have a single goal, then I want to basically say, okay, what's the shortest path from this start location to this goal? That's it. Maybe I have multi-agent, single goal. So this is the example of those tanks, right? And we have this group of tanks, and ideally we want that group to sort of stay together as it's moving toward the goal. Or maybe we don't. right? Maybe this one would take this path, this one would take this path. It all depends on what sort of parameters we pass into our pathfinding system to optimize it. We also have single agent, multiple goal. So this is an example of, say, you know, there's multiple different ways out of the maze, or there's multiple exits to a level, or maybe there's a bunch of diamonds that I'm trying to collect in a level. I'm trying to get to the closest one, etc. And so these are the different problems. Then there's the space and action representation. So space and action representation are important decisions because the ideas are linked. So for example, if you choose a graph as your space representation, it's probable that you no longer have arbitrary movements in your game. If you choose up, down, left, and right as your action representation, then your space representation should be able to accommodate that. So they're very correlated ideas, and they're linked together. Which representation that you choose is based on many factors from the game's design, right? So the game designers are going to tell you, the game programmer, okay, we think that the movement should sort of be like this, right? And so based on that type of movement that you want in your game, you're going to choose a representation based on that. The choice of space representation in the pathfinding engine will usually determine the movement actions that can be performed. So what do I mean by that? Well, here's some examples of that. So for example, here is an example where we have arbitrary movement. So there's nothing stopping us in this from taking sort of arbitrary movement in the level. We can move at any angle, whatever, right? So again, a nice example of that is like Path of Exile. For example, we can walk around in any direction that we want. So we could have smooth paths, we could have straight paths, we could have up, down, left, right, doesn't matter, we have arbitrary movement. Simplifying that a little bit, we could have straight line movement. So this is an example where we can only move in straight lines and then turn at sort of sharp angles, okay? Next, simplifying even further, we could have a grid-based system in which we can only move in 4 directions. So we can only move up, down, left, and right. In another example, we might have 8 directions, right? Where we could now move diagonally as well. If we constrain our actions even more, maybe we have sort of graph node movement. So we can only move in straight lines between these particular places in the environment. And so what we have here essentially is a graph with the nodes being these points and the edges being the legal actions between those nodes. So we might have a structure like this for our graph, and the only legal actions that we have are between these nodes on the graph. We could also have polygonal representation and polygonal movement. So what does that mean? Well, for example, here we have chopped up our environment into convex polygons. Convex is important because it means that we can actually see, if we draw any 2 points within any polygon, we can see inside this polygon. So what this does for us, if we have convex polygons, let's say we have a user right here in the middle, another point right here, that it means that any 2 points within each polygon, there is a straight line path that exists between them. So we know that if our start and goal are within the same polygon, then we can move directly in a straight line between them. But if they're not in the same polygon, then what we will have to do is we have these sort of these edges between polygons that say, okay, where are the legal actions between polygons? So if I want to go from this start to this goal, maybe I would have to do something like go to the middle of this polygon, then go to this polygon, then go to the middle of this one, then go up here, then go around and to the goal. Okay, so that's an example of a polygonal representation, and there's lots of interesting properties that come with this. We're not going to get into this one. It's a little more geometrically complex, but this is sort of what StarCraft II uses for its pathfinding system. So choosing a state representation matters. The memory size depends on the representation. The actions that are possible depends on the representation. The algorithms that are applicable depend on the representation. So we want to try and find a balance between the computation required to find a path versus the accuracy of the final path. So typically what we do in games is we choose a sparse representation for easier computation, and then later we refine the path to look more realistic. And I'm going to give an example of that a bit later in the lecture. Navigation meshes. So navigation meshes, what if my game sort of has an arbitrary geometry that I want to define somehow? So most game engines like Unity, Unreal, etc. are going to come with pathfinding systems built into them. And the way that you define the movement of your game is with a navigation mesh. So all of these representations that we talked about, they can be defined with a navigation mesh, meaning that all of these different types of representations we could represent via this thing called a navigation mesh. All we need to do is draw our meshes to represent this type of behavior. So a navigation mesh doesn't necessarily define the type of actions that are possible, but what it does is it allows us to create the type of movement representation that we have with a single data type, which is this navigation mesh. So for example, what if my game has arbitrary geometry? Well, we still need some sort of graph structure to enable our pathfinding within an environment. And the graph structure that is typically used by most modern game engines is called a navigation mesh, or a nav mesh. So most game engines, modern game engines, come with software to build and edit a level's nav mesh. And we're going to talk about a nav mesh much later. No, I'm going to talk about it right now. So here is an example from, I think, a very early version of Unity, where inside the editor, what we are doing is we are drawing the navigation mesh of a level. So you can see here that this is sort of the editor right here. And what we start with is this whole area that is completely navigable. So we have the whole floor is navigatable at the beginning, but then we sort of chop out the areas around these poles, for example. We don't want the user to be able to walk right next to that pole. We also chop out some things here. We also annotate the level and say that, okay, look, we can actually navigate from here on the ground up to this wall. And so what we are doing is we are defining how the user can move around in the level with this navigation mesh. And typically, whatever you see here as sort of blue-like, that is where the user is going to be able to walk in the level. And even if you have like complex three-dimensional geometry, we don't in our particular games, but if you do have complex 3D geometry, you can also define a nav mesh in 3 dimensions. So for example here, I think this might be, is this a video? No, it isn't. So this isn't a video, but essentially what we have is in this game, you can actually walk on walls. And so we've defined a navigation mesh here on this floor, here on this wall, and also we've defined little jump points that say, okay, you can actually navigate from this mesh to this mesh. And then anywhere within this mesh that's blue, you can walk. And so what we can do then is all sorts of crazy stuff. And so if we want the user to be able to jump between navigation meshes, then we can annotate parts of the mesh to say that, okay, if I'm at this part of the mesh and I move in this direction, I actually jump back and forth between these navigation meshes. And so here we can see, okay, we can walk up the stairs, we can walk on top of these things, we can walk anywhere on the flat part of the level. And so when it comes to navigation meshes, the hardest part typically is spending the time doing the markup on your level to actually define the sort of navigation mesh walkability that you want. But you can see here that we sort of have this graph structure, and anywhere within the flat parts we can walk. All right, so that is a navigation mesh. We are not going to be doing navigation meshes in this course, but in my next, in the follow-up course, if you will, to this course, we actually do make our own sort of navigation mesh and walk within that navigation mesh. So single agent pathfinding. Many graph search algorithms exist for finding shortest paths, each with their own properties. So for example, we have breadth first search, depth first search, Dijkstra's algorithm, A*, lots of different algorithms. Most video game pathfinding traditionally uses some variant of the A-star search algorithm. Now, we are not going to be implementing the A-star search algorithm in this course. It's not a required feature, so I'm not going to take a long time to explain it. However, I also have another course going on right now, which is an introduction to artificial intelligence, which is Computer Science 3200. And if you do want to know more than you've ever dreamed of about the A-star pathfinding algorithm, if you do want to say, for example, implement that in your project, I'm just going to mention the A-star algorithm here, but I give an ungodly amount of details about that algorithm in my other course, and all of those lectures are on YouTube as well. So if you want to know more about A-star pathfinding, by all means, go watch the lecture in that course if you want to. But as just a brief introduction to the A-star search algorithm, it is the most well-known best first search algorithm. It evaluates nodes by using two things, G and H, where G is the path cost so far from a current node. H is a heuristic function, so it's the estimate of the cheapest cost via this node. You have a function, which is f of n, which is the sum of these two. You have something called the open list, which is a list of unexpanded nodes. You select from that node the minimum f value, and you get this algorithm right here. So this is the A-star search algorithm. It is very, very easy to implement. However, I'm not going to go into the details of that because if you don't need to know the details of it for the course, and if you do, I have hours of content related to this algorithm in another course. You know what? I'm not even going to talk about an admissible heuristic because, like I said, there's lots of content about that in another course. So there's also a pathfinding demo that I can show you. So let me very quickly open this up, which is something that exists on my website. I'm going to copy and paste this into chat if you want to play around with it. But this is essentially a video game pathfinding system using the A-star search algorithm that I've made. So over here, I can choose a start location and a goal location, and this will show me the shortest path between those two locations. So if I load this up, for example, maybe we have, here we go, we have a bunch of caves that we're trying to navigate between, and there's the shortest path between those two caves. So if you want to play around, here's the A-star search algorithm, weighted A-star, breadth first search, depth first search, uniform cost search, greedy best first search. There are all sorts of search algorithms that you can use to do pathfinding in your game. And here we're doing them in this sort of grid world. Let me toggle off that grid, it looks a bit bad. In this grid world, so you can play around with that and see how these pathfinding algorithms work. This is not a pathfinding algorithm course, but again, if you do want to have pathfinding in your project, so in the project, what I described is that you either have to have some sort of non-trivial pathfinding or steering behavior, okay? I think that's what I said. I hope I didn't say and. So let me log in here real quick and see this. Let me see what I said. Whatever's in the document is what I said. Pathfinding theories. Some entities in the game must exhibit non-trivial pathfinding and smooth steering behavior. Okay, so it is an and. So there should be some non-trivial pathfinding. So whether or not that is like a breadth first search or an A-star or something like that, you have to have some sort of non-trivial pathfinding and smooth steering behavior. Okay, so keep in mind that you will need to do some sort of pathfinding in this course. However, I am not limiting you to the type of pathfinding that you want to do. Okay, so the pathfinding workflow, if your boss at the video game company or the designer comes over to you and says, okay, here's the pathfinding system that we want, here is the workflow that you will have in order to implement that pathfinding system. First, identify the problem that you're trying to solve, right? Is it single agent, multi-agent, single goal, multi-goal? What do I want to maximize? What do I want to minimize, etc.? You have to identify that problem first. Then you construct a space representation. So even if you're using a nav mesh, like are you using like a grid type nav mesh? Are you using like arbitrary representation, whatever? Then you decide on which actions are possible. Then you're given somehow by the game engine a start and a goal location. And you apply an algorithm which finds a path between a start and a goal location. And then you have to follow the path from the start to the goal. So it's not just one step. There's actually, this is a complex system in your video game once you're done with it. So let's have a look at what that might look like. Let's say we have this like 3D or 2.5D representation or map in our level. So the first thing we have to do, what was that? Identify the problem that you're trying to solve. So maybe my problem is just I have a single agent. I'm trying to get them from a particular start location to a goal location, and there's a single goal location. Okay, what's the next thing? Construct a space representation. So maybe I have a polygonal representation like this. And then I have to construct an action representation, right? So maybe my actions are, I can move from any polygon to any adjacent polygon. That seems reasonable. Next, I have to define a start and a goal location. And so here, I'm going to go from a start location to a goal location. And then I'm going to apply a pathfinding algorithm to that. So here is my pathfinding algorithm. It has returned a path to me. And then the final thing that I have to do, now that I have my path, is actually follow the path along the path that I've generated, okay? So that is pathfinding. That's the whole system of pathfinding, and at the very end, we have path following. Someone in the chat said if they can ask a question. So anyone can ask questions at any time, but what I do is I read them while I'm talking and see if they're particularly relevant. So if it's not relevant to what I'm saying, I'm not going to answer it, but you feel free to ask any question that you want. So back to the lecture. The last thing we have to do is path following. So once we've found a path, how do we actually make our agent traverse the path in the game? Well, the simplest way that I have found to do this is via a sort of waypoint system. So each point along the path we can consider to be a waypoint, and the path to the next waypoint is always clear, and I'll show you what that means in a second. So we are essentially just walking from one waypoint to the next, and we stop when the NPC reaches the goal. Okay, so when we reach the last waypoint, essentially. So here is a path following example. Let's say that we start up here, and then we have our goal down here. So in this representation, it's sort of a cherry-picked, really easy representation where I have a grid type system. And so the actions in this grid maybe are move up, down, left, and right. So what I've done is I said, okay, here are the actions. I move down a bunch, and then I move to the right a bunch, and then I get to my goal. So if I actually want to follow that path, what I can do is say, okay, this is the first waypoint. This is the second waypoint. So I'm going to follow the path to the first waypoint. Once I reach the first waypoint, I go to the second one, then I go to the third, then I go to the fourth, then I go to the fifth, sixth, blah, 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 right until I get to the goal. So I'm following the path along this path. Sorry, following the waypoints along that path. However, what we could do in our path following system is do something called path refinement. And the path refinement is done by the elimination of waypoints. So for example, this path here is equivalent to this path here. So I don't need to go like have a waypoint for every single action. I could say go from the start to this waypoint, then to this one, 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 right? So what I could go even further then is if my actual game wants to have like arbitrary movement in it, I could just say, okay, let's choose waypoints to be the furthest waypoint or the furthest action whose destination is still visible to me at some point, right? So let's say I start from here. I originally had waypoints at every action. What I'm going to do now is actually create waypoints along my path, which are the furthest possible action that is still visible to me from the start location. So I can go down and I can say, is this place still visible to me? Yes. Is this one? Yes. This one? Yes. 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 No. So this one is not visible to the start location. So the one previous to that, I could set a waypoint there. And if we look, we've reduced our path to like, here's one waypoint, and then we go to the goal. That's the final waypoint. So we've reduced 20 waypoints down to 2 waypoints, which is really nice. And then later, if we want to, if our game allows for sort of arbitrary movements, we could take this path, which has a straight line and a really sharp turn. And what we could do is refine that path to maybe, I don't know, some Bezier curve or something like that. And we could actually follow a smooth path toward the goal. Someone had a question. That is, the more points in the nav mesh, the slower it is to find a path. Typically, yes. So what we do with our representation, so if you take this grid, for example, the algorithm that we use for pathfinding is typically going to run on the size of the grid. And so if our grid, what we're doing is if we have many, many more points in the grid, or if our grid is finer, for example, if we take maybe the, 200 points in this grid versus another grid which may have 1,000,000 points, then the 1,000,000 point grid is going to take much longer to run our pathfinding algorithm on, but the results will be much finer grained, and so it may be like a better path in the end. So we're always trying to find the balance between ease of computation and the accuracy or desirability of our result from that computation. Okay. Oh, my throat is so dry today. Not sure why. Next, let's talk about another method for pathfinding called a vector field. So vector fields are also called flow fields, influence maps, vector maps. They have many, many names. They're a very efficient structure for pathfinding in the case of many paths to a single goal. Okay? So whenever we have many things that we want to go to a single thing, this is when we would use something like a vector field. So any case where multiple NPCs need to go to a single location, consider using vector fields. They are not always applicable, but when they are incredible. So we must balance computation with how many NPCs there are in the level. Okay, so let's have a look. Here's an example of a vector. Here's an example where we have many things that want to go to a single goal location. And the best example I can find of this in an actual video game is something like an action RPG like Path of Exile or Diablo, for example. So if you have Path of Exile or Diablo, you have a single player running around, and you might have 1,000 zombies on the level that are all trying to get to the player. And so are you going to run A* for all of those zombies to your player? I don't think so. You're not going to run 1,000 instances of pathfinding. What you're going to do, ideally, if you can run a vector field type pathfinding system, then that would be ideal. So it turns out that with one calculation, you can calculate the paths of all of these little light sources that are going towards the player's mouse. You can do that with one pathfinding call, which is super nice. So let's go over sort of a high-level view of how you would do a vector field. If you're interested in vector fields, this is actually one of the assignments in my other course, 4303. So step 1, you create what I call a distance map. So a distance map is if you have a goal location, okay, like for example over here, or a start location, the distance map, now that may be called something else in another website or other literature. What you do is you do a breadth first search outwards from this point, and you record how many steps of breadth first search it took you to get from another location to this location. So for example, from the start location, it took me 1 step to get to this cell. So I guess the very first thing you do is you break up your environment into a grid type representation. And then you have all these distances. So for example, this spot right here takes 7 movements to get to this spot. So 6, 5, 4, 3, 2, 1, 0, right? Next, what you do is once you have this distance map, you're going to take each number, each cell, you're going to draw a vector from this cell to the neighboring cell with the lowest number, okay? So this is what you end up with. You end up with this 9 pointing to this 8, this 7 pointing to this 6, this 3 pointing to this down here. And then what you have is you just need to follow that direction to reach your goal. And you're done. Isn't that crazy? So like you construct this vector field and you have constructed the path direction for any entity on any part of your level to reach a particular goal location. And so if you look, this is exactly what's happening in this case. Whenever we move our mouse around, whenever we click our mouse in this environment, we are computing a distance map, and then we are also computing this vector field. And then all you have to do to reach your goal location with any of these entities is calculate the vector field calculate where you are in the grid, look up the vector field direction, and then just go in that direction. So that's really cool how you know, the pathfinding system we use for single agent versus multi-agent might be completely different. Because if you just had a single agent that wanted to get to your goal, then a vector field is overkill, right? It's too much computation to do for a single thing, but if you have 10,000 things that want to go to a single goal, then this is great. So the last 4 slides came from this website. So if you're really interested in vector fields, you can totally go look at this and implement it for your project if you want. Influence maps are very closely related to vector field. However, what they do is they also incorporate more logic than just a simple distance to a goal. So an influence map will usually use a vector field as its final representation, but an influence map is used to say, for example, I want to avoid something on my way to something, or I want to be drawn toward these things. And I'll show some examples. So it's used when it's difficult to come up with an objective function for other algorithms. So for example, if we want to figure out, if we want to keep our distance from some attacking enemy, or if we want to make sure that our path avoids some walls or something like that. So it's best to just show you an example of an influence map. So here we go. Let's say we have a starting location over here on the left and a goal location over here on the right. And we want to pathfind from a start to the goal, but we don't want to touch the enemy. Okay? So what we do is if we computed this distance map, like what we did for the vector field, then we would just avoid stepping on the tile where our enemy is. Okay, so that's the simplest possible example where we just avoid a tile and we go around it, right? So here, instead of going 1, 2, 3, 4, 5, in order to get here from our goal, we would go 1, 2, 3, 4, 5, 6, 7. So we go around something. So we essentially just block something in the map in order to form the influence. So it's positive influence in some cases, negative influence in other cases. If we want to avoid something, that's a negative influence. If, for example, we wanted to avoid, let's say we're in a boat and we want to avoid going too close to the shore because maybe there's shallow water or sharks or something there, right? Well, what we could do with our influence map is start with a big value next to the place that we want to avoid. And then what we would do is we would say, okay, well, look, now that we have a bigger value here, we are going to avoid these areas. So if we absolutely are stuck, then maybe, yes, we would go through this area, but only if a safer thing didn't exist. So this is another example of like a repulsive force for an influence map. Also, maybe we could have something like a turret here. So an enemy that has some sort of attacking radius that we really want to avoid. So what this says basically is like, I would rather go 50 distance away from here than travel through this area. And so when we form our final distance map, we have a seriously big area of negative influence around this area, and we would really avoid this area when we go to our goal. Now, That being said, influence maps are not as simple as what I've given you right here. Oftentimes, like deciding on the influence and the formation of the map and the path following is a little bit more complex than this. But this is the general idea of an influence map and what it does. So I just wanted to give you that, so if you ever saw it out there, you'd know what they were talking about. Okay. The last thing I'm going to talk about this lecture is something that you do have to implement for your project. And so this is a really cool thing. It's called a steering behavior. And steering literally means steering like in a car. Okay? And you'll see why that is quite soon. So steering can be seen as a framework for controlling autonomous agents such as robots, CGI in movies, NPCs in games. And what steering does is it adds more realism and fluidity to agent movement, and it can enhance the experience for the player. Steering can be really fun to implement. I love playing around with steering behaviors because you get to play around with these parameters of the steering algorithm, which we'll show in a bit, and see what sort of effects that can be produced. So at its core, what steering does is it smooths the movement of entities in games, and it guides behavior either toward or away from something. So changing directions instantaneously in a video game can look really bad, right? So sort of stopping on a dime, right? So for example, if I'm following a path like this, and then I just take a turn like that, there's no better giveaway that there's a poor movement system or like janky AI than walking in a straight line and then turning on a dime and then following the path again. You've all seen it in video games. So steering acts as a sort of a force that smoothly guides your entity toward a target. So up here, instead of this straight line stop on a dime, what steering is going to do is sort of smooth that behavior so it acts like this, okay? And this will be part of the project. Don't worry, it's not as bad as it sounds. It might sound really complicated, but it's just a few vectors, right? Just a few vectors. Here's what a steering behavior actually looks like. Or here's the math behind a steering behavior. We're given an entity. That entity's shape doesn't really matter. We're not talking about collisions or anything like that. So I'm just going to represent it by a square, circle, whatever. That entity has a current velocity, meaning that on the next frame, you're going to update the position by this velocity, right? So it's currently right here. The next frame, it's going to be up here somewhere. But this entity has a desired target, right? It has a direction that it would like to go in. So for example, let's say that my entity is currently walking around the game. I'm just walking around, walking in my straight line, minding my business. And then maybe I'm an NPC, then I see the player. And my directive is to, if I see the player, I want to attack the player, right? So what I could do, if I see the player, now I have a desired direction, a desired target that I want to reach. Well, what I could do is just change my current velocity to be this desired velocity, right? So I see the player, I'm going to keep my same speed, right? So this length of the vector is going to stay the same, but I'm going to immediately point toward the player. Well, that is the behavior that we want to avoid, is walking in a straight line and then instantaneously turning and then walking in that straight line, okay? But this is actually a part of figuring out the steering. So here's the math. We have our current velocity and we have our desired velocity. So this is called desired, this red one. And so how do we keep the desired, or how do we calculate this desired vector? Remember that we wanted to, we've already covered this math in the lectures, right? So we're not going to spend too much time talking about the math, but if we want to go from our current location to a desired location, then that is my destination minus my source. So that is target minus position, right? So target minus position, that is the dashed red line. That represents the line that goes directly from where I am all the way to the target. but I've got some current speed, remember? I've got some length that I can travel every frame. So now I'm going to have to scale this dashed red line to meet the red line. So what we do is we normalize that vector to bring it down to length 1, and then we multiply it by the length of my original velocity, right? So I have an original velocity, the length of that vector is my speed, so I take this red dashed vector, I normalize it to bring it to length 1, and then I multiply it by the length of this vector to make it the same length. So now I am left with this. Here is where I was currently headed, but here is where I want to head, in this direction. So if I want to get from my current velocity, the end point here, to the end point of the desired location, then here is how I would do that, right? I would go along this green vector. So this green vector is actually going to be our steering vector. And you can think of steering as you being in a car with a steering wheel, as I said, right? So in a car, if I can, I'll go back a slide so I can draw. If I'm going in this direction, right? If I'm going in this direction, if I'm currently in a car, not an NPC, but in an actual physical car in the real world, and I'm going in this direction, and then I see my target over here, like, oh, maybe there's that guy I don't like. I should run him over, right? That's a terrible joke. But, or maybe, oh, ice cream truck. I want to go towards the ice cream truck. That's a little more applicable, right? A little more education friendly. So I can't just instantly turn in a car. There has to be some radius of turn in a car like that, right? That is what steering is going to do. When you turn the steering wheel, your wheels turn a little bit in the direction that you want to go. So that is what this steering vector is. If I want to change from my current velocity to the desired velocity, the green line will take me all the way 100% from my current velocity to my desired velocity. And if I want to calculate that, it's destination minus origin, so it's desired minus velocity, right? So the desired minus velocity gives me that steering. But if I went all the way from my blue to my red, then that would be that stopping on a dime, really jerky movement. So what I actually want to do is have this actual vector. And so instead of going all the way along this green vector from my current velocity immediately to the red velocity, we are going to scale the steering vector. And that is the steering force. Okay, so the scale of that remember when we applied scales? We've already talked about scales of vectors. We're going to multiply this by some value between 0 and 1 to give me a shorter vector in the same direction. And if I add that scaled force to my velocity, then I get actual velocity. So actual here meaning where I actually want to go on the next frame, right? So, what's this next? Okay, the next slide didn't do anything. So how do we calculate that? This is the steering vector. I want to calculate the steering vector so I can add it to my current velocity and change the direction of my movement in a smooth way. So calculating the actual vector, how do we do that? Well, we are going to choose some scale. That is, we're going to experiment. Choose a number between 0 and 1. Maybe it's 0.1, maybe it's 0.01, right? And so you're going to be turning, the higher that value is, the jerkier your steering is going to be. The lower the value is, the more gradual your steering is going to be. So we choose some scale, and then steering, initially this dashed green line, that's going to be desired minus velocity. Then the steering vector, which we had desired minus velocity, we multiply that by the scale. And then the actual vector is just my original velocity plus the steering velocity. So that's all that it is. Here's the math behind that. I've got this up in the corner. So I've taken this diagram and shrunk it and it's behind my face, but you'll see it on the PDF. That's okay. So given your current velocity, given a target where you want to go and given a scale value or the steering force, what you do is you first figure out the dashed red line, which is desired. Then you make desired, you normalize that by dividing it by its own length. Then you multiply it by the velocity, the blue one's length, to get the same length vector pointing toward the target. Then your dashed green line, steering vector, is desired minus velocity. Then you scale the steering vector to be some pleasing value length. Then, in order to get the actual vector, you have velocity plus steering. Look at how easy that is, right? So that's steering. That's it. That's the math of steering, and it's super easy. And if you want to implement that sort of smooth movement in your games, then you just implement this formula. It's a few vector additions and scalar multiplications. All right. There are, however, types of steering. So we've seen that we have a current velocity and we have a target. If we do what we just did, then if our desired vector points directly at where the target is right now, this is called a seeking behavior because we are seeking exactly where the target is. If, however, our target also has a velocity and we want to sort of meet up with the target where it's going, if we make our desired vector point toward the target's velocity vector, that is called a pursuing behavior. So that actually looks way more realistic in some cases. Like if I want to go toward a moving target, I shouldn't be aiming where they were. I should be aiming where they're going to be, right? So that is a pursuing behavior. If, however, if my target just appeared and they're a big scary monster, maybe I actually want to flee instead of head toward them. So if I take my desired vector and I just flip it by flipping the x and y, so I just negative both of those, then I have a flee behavior because my desired behavior, instead of moving toward it, I'm going to be going away from it. And so you can flee using steering as well. So steering can actually be used as this sort of like pseudo pathfinding type of system, which is really interesting. So what I'll say is that if you use steering in multiple ways in your project, so for example, if you use it for seeking behavior and for fleeing behavior or for avoiding obstacles, then I will count that as your pathfinding as well. So if you use steering in a very interesting way, that could also be counted as your pathfinding system. I'll give you a little freebie there. The last thing when it comes to steering is what happens as you arrive toward your target. So one issue with steering is that the closer you get to the target, the entity is going to oscillate. What does that mean? It means as I arrive, so up here in the top right, as I arrive toward my target, there's this vector. So if this is my target, I have a vector toward that target, right? I'm going to be going at a specific speed. If I overshoot my target a little bit, then on the next frame, my vector is going to be pointing in the opposite direction, and I might overshoot it a little bit again. And so it gets this overshoot, 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 overshoot. And what you see is it's a behavior like this where it goes toward the target, go towards the target, and it's like boom, 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 boom. And so that's a little bit annoying, and it's not what you want in your game. So what we have to do, let me get rid of that drawing, is we have to define what we call an arrival behavior. So what happens as we get closer to our target? So the simplest solution is just to scale the speed linearly as it approaches the target with some distance. So my example of this is as you're pulling into a parking space, right, you're doing steering behavior. You have a desired direction, you're steering with your car. However, if you were driving like 50 kilometers an hour toward a parking space, ideally you're going a little bit slower than that. Let's say you're going like 30 through a parking lot, which is still pretty fast. You're not just going to like drift into your parking space and go from 30 to 0, right? You are going to, as you get closer and closer and closer, you're going to go slower and slower and slower, and eventually you'll stop, right? So if we scale our speed, here you can see that as we're moving closer to the target, these triangles are getting closer and closer together. So that's what's happening there. We are actually scaling our speed to be lower as we get toward the target. And there's no best algorithm for this. You just have to try it. Try a steering behavior. Try different steering forces. Try different arrival behaviors, and you'll see. Someone says, you don't park like Ace Ventura. Yeah, when he flips the Jeep into the thing. That's a good reference. Yeah, we don't want to park like Ace Ventura. All right. So here's an example of a seeking behavior, right? So we've got a little kitty cat here. This is an example I saw online, and we're clicking the mouse toward the kitty cat wants to go, and the kitty cat is going with some steering behavior, and you can see the nice sort of turning radius that you have. So that is all done with the steering behavior, and it's really nice. Avoidance steering can also be done for like sports games, right? So this avoidance steering, if I'm currently going this direction, but I want to avoid running into the defenders of the other team, I can actually have an avoidance force in this direction as well. Something that I have not seen in a project yet, which would be really cool, is a sports game. I have not seen anyone make a sports game, which I think would be pretty fun for the project, but you still have to have all the different, I guess, if you have a sports game and you need to have 3 different guns in the sports game, maybe that's not the best idea. Maybe that's why you haven't seen it, Dave. Okay. So yeah, you can use avoidance steering like this. Here is a really cool example using steering where you have like this sort of traffic jam, and we have different rules for like heading toward our goal, but we also want to avoid enemies, right? And so this is just using steering. There's no other pathfinding being done here, and we do see eventually that they sort of work it out between themselves using the steering by avoiding each other. If you want to see more about steering, there's a really cool project called OpenSteer, and OpenSteer has a bunch of other demos. You can download it. It's really cool. I'm not going to show it now, but feel free to look at that as inspiration for your project. So that is it for today. We have talked about pathfinding. We have talked about steering. In the next lecture, I'm going to talk about game tools and drag and drop. So as I said, one of the major parts of your project is going to be a level editor. And in order to have a proper level editor, you're going to want to be able to drag and drop stuff, right? And so I'm going to show you, talk about game tools and how you pick up things, how you drop things to make your level editor. Someone said I have some typos. Thank you. Where was that? Okay, so I had some typos in a couple of slides. Thank you. I'll try and fix those right after the lecture. And yeah, that's it. So thank you all very much. Your assignment 3, I guess, is due 1 week from right now when I'm giving this lecture. So make sure that you, if you have not started assignment 3, you are in trouble. Assignment 3 is a lot of work. So please start assignment 3. And I'm really looking forward to seeing your project ideas. So please submit your, we had, what did I call it? The project proposals. Get the project proposals in as soon as you can so I can give you that feedback as soon as possible. Great. All right. I hope you all have a great weekend, and I'll see you on Tuesday for the next